All right, well, it's really exciting to get to introduce Joshua Mathew, who's going to be presenting today his capstone project on designing an FPGA implementation of parallelistic decoding for CRC-aided convolutional codes. So Joshua, it's really been a pleasure working with you over this year, and I'm going to go ahead and let you share your screen and you can give your proposal or give your project report. Thank you.
Can you share my screen? Oh, can you enable?
Oh, you're right. Let's do that. Okay, try it now.
Can you see my screen? Okay, perfect. Hi, I'm Joshua. I've been, for the past 2 quarters, I've been working on hardware acceleration for some.
Hey, I'm going to mute and you unmute now, and that way we'll get better.
Hello, am I audible? Oh,
yes. There, go ahead.
Perfect. Hello, I'm Joshua. I'm gonna go present my work in CSL on hardware acceleration of list decoding, and I like to mention that a lot of the work is based on Chester Hulse's work in his master's project. And then at the end, there's also like a little section on noise generation. All of this, first I'll kind of give background on list decoding in general, and then I'll kind of go into the architecture of the implementation of the decoder and some noise generation on an FPGA. Just to start off, I'll give a background. So firstly, I'll talk about convolutional encoding. So I think most people here know what encoding is, so I'll kind of skip the what is forward error correction, but a convolutional encoding kind of is a type of forward error correction that does a convolution on a stream of bits that we're trying to send using some binary polynomial to produce an encoded message. So on the left here, we see kind of like and we have an example on the right of like how a convolutional encoding might be made from a message you want to send. For example, if you want to send the bits 1, 0, 1, 0, given some polynomial that we use to encode, we kind of perform this sliding window operation on the incoming bits and then produce using the polynomial and that window, we kind of generate these encoded bits based on the stream. And this is actually really simply implemented in hardware. For example, if the polynomial that we want to convolve is this sequence above, we can kind of visualize this as storing 3. If the bits are coming in on the left, we can kind of visualize this convolution and the sliding. The most recent bits that we're trying to send in memory, and then performing this polynomial on those stored memory bits and the next bit that we were trying to encode. And each time we get a new bit that we're trying to encode, that kind of produces a new encoding. And a very good conceptual understanding, or a good thing that we can think of these states or these memory elements being is representing a state. And every time a new bit that we're trying to encode comes in, it kind of updates the memory elements and therefore updates the state. And like a representation of how the state transitions over time, it can be visualized with like a trellis. So on the right here, if you can imagine the blue memory elements being like the numbers 0 and 1 that are in those memory elements, then these states, these nodes in this graph kind of represent what the state of those memory elements are, all the possible ones. For example, if we had 3 memory elements, there are 2 to the 3 possible states we could be in. And depending on the bit that we're trying to encode next, it kind of switches us from one state to the next. So the trellis kind of over time, a path starting from the left to the right kind of dictates all the state transitions that happen, and therefore dictates the message that we're trying to transmit and encode. And if we label each edge based on the polynomial and based on the bit that we're trying to send, if we label each of these edges with those, we can kind of associate each path in the trellis with a particular encoding and a particular message that we're sending. So that kind of goes over the encoding portion. If we're on the receive side, we kind of assume that, or one method of decoding this type of convolutional code is trying to find our overall goal is to try and find or trying to find a sequence that most matches what we receive. So based on the trellis representation, we can kind of think of that as what is the best path in this diagram where the encodings of the path most match the received message. So this is effectively a maximal likelihood path, like what is the most likely path that matches what we receive. And the method of figuring out what that path is called Viterbi decoding. And a particular implementation of Viterbi decoding is called parallel list Viterbi decoding, where we kind of iterate through the time points in this trellis, like from left to right. And then each time that we each time that we go from one time point to another, we keep a running list of the best paths so far that match what we receive. So kind of each of these edges will have a list, and then at every state, each state will always have two incoming lists to it. And what the parallel list Viterbi decoding algorithm does is it compares those two lists of paths, picks the best paths out of those lists, and then passes it on to the next time point. And then on each edge, now each edge has a particular list of paths, and it compares the encoding associated with that edge to what was received in that section, and it adds the distance of that difference between what was supposed to be encoded versus what we received to the metric of determining like how good a path is. And we kind of keep on doing this until we've reached the end of the encoding and we have a list of the best paths. And then from that, we pick the best one and we say, oh, this is our most likely, this is what we received. But there are also like additional conditions that we can place on the message before we transmit it that make it have an even better success, like in practice. One condition is a tail biting condition, which is basically it's essentially a way of syncing. So in reality, when we send these messages, we can't, if we wanted to send a really long message, what we would want to do is break that message up into frames, and then like keep sending frames. But in order for the decoder to understand that, like, oh, this is a frame versus this is a different frame, it has to kind of be in sync with the encoder, or be in sync with the transmitter. So a tail biting condition is a condition that kind of says, okay, the messages that we send, each frame is gonna have the same starting state and ending state in the encoding, and it's going to be a fixed length frame. So when the receiver receives a frame, it can check whether the start and end are the same state, and then every frame from there, since it's a fixed length frame, it'll be synchronized with the transmitter. Another condition that we can place on the message is adding a CRC portion to it, and that effectively is something that we can add to the message that after decoding, it can add further error correction and error checking to ensure that the message that we sent is what we wanted to send. So yeah, that's kind of an overview of list decoding, and I think this project particularly aims to accelerate the parallel list Viterbi decoding algorithm for tail biting codes that also have CRC. So this there's a couple optimizations that we can kind of make off the bat. First is in our metric, when we calculate the metric, in reality, when we compare the code versus the encoding, what we're actually comparing is the log likelihood ratios of those at the receiving end. So we choose the metric to compare those two to be Euclidean distance, and that can be simplified since our encodings are always plus or minus 1 because we're assuming that we're modulating with BPSK, and since our log likelihood ratios are always the same at each time point, because the received message doesn't really change at each at each time point, this received message will always be the same. So that part of the calculation is also simplified, and it's because it's constant. So in reality, what this Euclidean distance metric can be simplified to is just maximizing the multiplication of these two log likelihood ratios. But in hardware, this is even simpler because since C is always plus or minus 1, all we have to really do is take the log likelihood ratios of each bit in the received message, flip them based on what the supposed encoding is of that edge, and then add that to the ongoing metric, and then keep on going forward with the computations. The other hardware optimization we can do is since the goal is to kind of keep track of the best lists and filter out ones that are incoming to each state, if we maintain the lists in order of how good their metric is, of like how good the paths are with metric, we can kind of perform this merge sorting filtering where the job of the part of the list decoding algorithm is to look at these two lists and then pick the best paths. And if they're sorted, this becomes easy because we can just pop the top, or like we can just look at these two lists, pop the best element off and add it to the next one to pass it forward. And then similarly, in the next cycle, we can just look at the top of these two lists and pop the best one, add it to the cycle, or add it to the ongoing path, and then so forward, and then keep on doing that. So that makes the filtering part really computationally efficient, and this makes the metric part very computationally efficient in hardware.
I have a question on the previous.
Oh yeah, go ahead. Which one?
Closer to his microphone, so.
Oh yeah, which one?
Yeah, I'm just not clear what. So in the plot, in the diagram,
This one.
you have two input lists.
Mhm.
So what are these two?
Yeah. So what are the numbers?
No, I
What
know
are
the
the-
numbers are the
Yeah,
metrics.
yeah.
But what do they represent for? So yeah. So I think that is what I don't understand.
So the numbers are like as in. So we understand that it's the metric, but
Yes. It's metric for what? So
it's
yeah.
the metric for. So for example, let's say this is the trellis, and like we're at this time point. This filtering would be kind of this filtering would be done at each state, and each state has two incoming lists, and the lists store the metric that of like every path to get to, or all the L best paths to get to that point in the state, right? And then since there's two edges incoming, there's gonna be two lists.
I
And
understand.
then
So but let me ask this clarifying question. The merge sort happens after you add the most recent branch metric so that you get updated path metrics to the final state.
Correct, yeah. So in the previous time point, maybe you filtered to L and then,
Merge sort, filter.
oh yeah, so we merged sorted to L, and then on this outgoing branch, we kind of add that branches or add that edges metric based on its encoding and that section of the received message. And then similarly, this edge will have its own, this edge will have its own metric that's added to each separate list. And then those two lists will be sorted at this state. Does that kind of make sense?
It makes sense.
Okay, perfect. So yeah, so that part is made efficient with these optimizations. So now I'll kind of go over the previous design.
Your R5 is equal to CI plus noise, right?
This would be, yeah.
Observation. Okay, so
Yeah.
why you call it LNR? Because LNR means that if you have CI equal to plus minus 1, you should multiply observation by 2 or sigma squared.
Yeah, there's a little blurriness between the equations that you have in the vector computation are for a metric. And actually, I don't think you're ever really computing an LLR. That's left over from the LDPC project where we talk about LLRs. You're just passing along these metrics. They're not log, we're never taking a log.
Aren't the inputs to the decoder log likelihood?
No.
Okay, I get that. That was kind of the understanding from the previous implementation, was that at least in the previous implementation, the assumption is that you're getting the log likelihood ratio of like what the
Well, the Euclidean distance is a log likelihood ratio. Or
Not a ratio.
not a log.
It's a log
it's
likelihood. Likelihood, okay.
Okay, but when you switch to the max,
Mhm.
it's no longer the log likelihood, it's just another number that
Okay,
is monotonic in the same way. So if the log
Okay.
likelihoods are ordered the right way, then that number will also be ordered the right way. But, so I think that, like, the correction to the slide is just
Mhm.
not even say log likelihood and just say metric. Because everything else is correct. So the top thing is a metric. It happens to be a log likelihood or within a constant of it. And then the second
when you say
thing,
the top thing, you mean this?
yeah, that.
So would the
Because-
received message not be in the form of a log likelihood ratio?
No, the received message is just bits. You get the R's,
Got
they're noisy, just like
Yeah,
Professor
yeah,
Dixlar said.
Yeah.
We transmit plus or minus 1.
Yeah.
What do we get? Plus or
Plus or
minus
minus
1 plus Gaussian noise,
Yeah.
just like you generate the Gaussian noise to do that. So
Mhm.
that's all we get. And then we're literally gonna take what we received, subtract what we expected, plus or
Mhm.
minus 1,
Mhm.
depending on the branch, and square it.
Okay,
And
yeah, that
The
makes
reason
sense.
why so you could just think of it as a metric and never even talk about the fact that it's a log likelihood. But
Mhm.
because the likelihood, it's a Gaussian distribution, which is 1 over the square root of 2 pi sigma squared times e to the minus that squared distance over 2 sigma squared. If you take the log of that, drop some constants, forget about the sigma squared because everybody's got it, you'll end up with squared Euclidean distance.
Okay.
So we're computing squared Euclidean distance.
Mhm.
It's a metric.
Yeah,
It is closely related to the log likelihood, but not
It's not
really
exactly.
because we dropped some constants and scale factors.
okay. Yeah.
And then we further manipulate it by saying, oh, we only need this product.
Mhm.
So it's not a log likelihood at all, but if we find the best sum of these products, whatever that answer was, would also be the answer that has
Yeah.
the best likelihood had we
Yeah.
computed it.
Okay. Yeah,
So
makes
thank you
sense.
for
Yeah.
clarifying that, Professor Dixlar.
I have a second question.
Yeah, go ahead.
Is the filtering, the module
Mhm.
easy to realize in hardware?
Yeah, so there's kind of 2 implementations that I'll kind of go over actually. I feel like the next parts will kind of go over it. So so the overall design is you'll get your inputs and then there's this module that does the parallel list decoding part. Then at the end of that part, you kind of take all of your best, you have like S times L of the best lists or the best paths through the trellis. And then in order to make sure that the paths are tail biting and pass CRC, they go through these kind of funnels that basically select the ones that, or select the, out of those big lists of paths, select the ones that are tail biting and select the ones that pass CRC. And then of those, we take the minimum or the best metric one, and then say that that is our maximum likelihood decoding. And then this module that does the parallelistic decoding in the previous design. So there's kind of two ways that the list maintaining can be implemented. The first one, which is what Chester did in the previous implementation, was you kind of implement it as a first in, first out memory structure, where your list is, since you're doing the merge sort, right? The first in will always be the best metric, and then you always pop the best metric out. So that is easily implementable on an FPGA and in hardware. And in fact, that's actually the most logical way to do this in like a data structure perspective. So that was what was done. So in this design, there were two of these first in, first out memory structures per state that kind of stores the L best paths. Also in this design, all the state computation, so like all of these were done in parallel. Like there were S 2 to the N or S parallel branches of computation. And it kind of, the benefit of that is like there's fixed routing from the state module. So there'd be S of these, and there would be fixed routing to each of those modules. And also there's fixed routing from the edge to the states. So the edges handle the metric part of it, and the states handle the merge sort part of it. The issue with this design was that one was the first in, first out memory structure, while it like makes sense on a data structure perspective, it actually kind of wastes a lot of cycles in this computation, because imagine a scenario, which is actually pretty common, where one list has L better paths and the other ones just have L worse. When you do this merge sort, you're just always going to pick, everything you pick is from one list, and then now you have to flush out the remaining paths that you don't use from the other list in order to go to the next time point. And that kind of wastes, basically doubles your computation time in that scenario, which is the worst case scenario, but it's a little bit wasteful. And then also an issue with this design was that for high state encodings, it would use too many resources on the FPGA, because the number of memory modules that were instantiated scales with the number of states needed in the code. So in this example, we kind of had on our FPGA board, we were trying to decode with 256 states. And in this design, that would attempt to instantiate 512 like memory, like FIFO memory modules. And basically with that, it's more than the FPGA has. So then it tries to do some other things to make up for it. And it just creates a lot of like issues that make the computation actually slower than expected. So in order to address this, the changes to the design were, instead of making there be a memory module, or instead of trying to do everything in parallel, we're gonna make a parameter be like how many BRAMs we want to use. So one benefit of that is we can kind of like modularize how much resources on the FPGA we want to use specifically for decoding. That's one benefit. The other benefit is it kind of makes it also allows us to shift to this addressable memory implementation. So I'll kind of go over that. So firstly, we kind of assume that we can only use KBRAMs, or which is the memory modules, and because of that, we're forced to do we're forced to add some sequential processing to the PLVD algorithm instead of doing all the states at the same time. So now in order to maximize the KBRAMs we have K parallel branches of computation, which means that we have to split the states that we're processing into like E over K iterations. So for example, in a scheme where we have 8 states and we're only allowed to use 4 BRAMs, we would kind of like want to split the cases into we would do 2 states at a time, which would take 4 iterations, and we'd be processing 4 edges at a time, if that's what happens. And then instead of using a FIFO memory structure, what we do is we have a fixed memory structure where the BRAMs are now addressable memory. It's not in this diagram, but in reality, there's like 2 sections of memory. One where we read old paths and metrics, which then get placed into the next section of memory that are the updated ones. And this
Our file is addressable memory.
Addressable memory is like
You can find
like
address.
before it was like FIFO, right? Meaning we just you can only like pop data off the top and add it to the bottom. Addressable memory is like, I want to look at this address
It's a
in RAM. It's RAM.
Ah,
Yeah,
I see,
RAM.
I see.
Hence the name VRAM.
Yeah,
Uh-huh. Yeah.
well, yeah,
Okay.
yeah.
How many bit quantization are you using for your observation to the decoder?
I think it's 72 bits, but so the answer is it's modular, like depending on how long your
No.
I don't think he's asking for more.
It can't put representing the bit.
The plus or minus 1 plus noise, how many
Mhm.
bits do you use to represent that? That's what he's asking.
Using floats, fixed precision, how
I
many
think it's
bits?
fixed precision.
How many bits?
I want to say 32, but
What? Quantization?
I think so.
Much.
Screen precision.
I think inside the decoder, whatever the input is, it gets
Okay.
truncated. Yeah. So at the end of the day, what's getting passed around is only, I think, I know each object which contains information about the path and the initial state are only 72 bits. So there's a section, I don't know what the actual number is, but only a section of that is dedicated to the metrics and the quantization of the metrics. If that answers your question.
I wanted to see that the observation that you receiving to the decoder, you
Mhm.
have to quantize that, you use
Mhm.
quantizer.
Mm-hmm.
How many levels or bits of quantization?
I don't have the
Is it
I don't
3 bits, 4 bits, 5 bits. Usually, 3 or 4 or 5 if you have.
I don't think I have the answer to that, but I can get back to you if
Okay.
you want.
You're using this for simulation?
Eventually,
Yeah,
once
that's
it's
the
working,
goal.
we will see it.
Yeah.
Because what matters is like, how do you represent the noise?
Mhm.
And that, I'm guessing you're gonna use the same precision
Yeah. Or
Well-
you have registers
Yeah.
of everything, right? What is the size of the VRAM? Is it
oh,
bytes?
it's
Is it-
so actually depending on your FPGA, it would be, you can like configure how wide your VRAM is. So in our case, we maximize the width because there's a lot of other information we want to store. So for us, it's 72 bits.
So this is a parameter that you can configure on your code. That's what you're saying.
Not really, no. Well, are you talking about the metric or the VRAM
No,
width?
the VRAM, how many each
Yeah,
entry on
yeah,
that table?
yeah.
How many bits of width
it is, right? So
So-
let's say
yeah.
VRAMs, let's zero has right there in your table has 4 entries, right? Each entry is gonna be a byte, 2 bytes, or anything else, something else?
Yeah, so it's, for us, it's 72.
Oh, okay.
Yeah.
Good
Does that
question about
answer-
the CRC
okay.
codes.
Uh,
About the
So you,
CRC.
when you do the metric, when you compute a metric, you represent the metric with 72 bits.
no, so what's stored in memory is a combination of the state,
Metric and
state-
states, there's a whole bunch of
yeah.
stuff. So
it's like,
unfortunately, that's right, there's a whole data structure he's passing, and it's a simple enough question for him to answer, but he has to go back and look at the code for him to know the answer.
yeah, I don't know what the actual numbers are for what in total it's 72 bits, but how many bits are each part of the object, I'd have to look.
Okay,
Yeah.
thanks.
Yeah.
Regarding the
okay,
CRC
yeah,
bits,
so
do you use it for
the
error
design now
correction or
becomes,
error
instead of doing
detection?
everything in parallel, we maximize the parallelism that we can do with the number of VRAMs that we're allowed to use. And to do that, we add some sequential processing, and we also now shift to like RAM, addressed memory, instead of a FIFO structure. But this kind of introduces like a design challenge in that, let's say with this example, let's say we use this example where I ordered the state processing in this way, and I put the VRAMs in memory, or put the edges in memory in this way. On the very first state, we'd be processing state 0 and state 1, and we'd be trying to read edges 0, 1, 8, and 9. But in memory, edges 0 and 8 are in the same VRAM, right? Based on my arbitrary association, and edges 1, 9 are in VRAM 1. And then VRAMs 2 and 3 get no reads. So that's pretty inefficient in a whole scale situation, especially when there's a lot more states, a lot less VRAMs, and a lot more edges. So the goal is we have to create some kind of system where each VRAM will get exactly 1 read and 1 write, given the trellis structure. How we have to A, make a state processing order, and B, put the edges, store the edges in memory at a fixed address, such that we can only have 1 read and 1 write, and we can access, and we know where each edge is. So the solution to that was kind of a brute force. So it was somewhat brute force, but there are some key insights that made that a solution possible. One is actually kind of neat and nifty, is that so the goal is to basically put these edges in a particular VRAM and distribute them evenly, right? Another way you can think about it, though, is just we're assigning each edge some number that represents the VRAM that they're in, right? So like, for example, here, edge 6 is in VRAM 2. But if we represent VRAM 2 as in bits, like bit 1, 0, that effectively is just the same thing as creating an encoding for an edge, right? And we already have a representation of encodings for edges, which is this. Like, convolutional encoding in and of itself kind of gives us a way to think about how to encode edges in this trellis structure. So that was like kind of a key insight. Basically, the problem simplifies to how do we find a generator polynomial such that each edge will have 1 read and 1 write from a VRAM. So every time. And so the overall solution is kind of, we do the naive ordering from before, where we kind of just we process like the states in order based on how many VRAMs we have, and then we also and then the second part, which is the VRAM labeling part, we found that this specific generator polynomial is consistently gives us a successful labeling of the edges, such that the edges or such that each VRAM is read or has one read and one write every cycle, given this ordering of processing the states. So yeah, I think the proof for why this works can be given. I don't know if it's necessarily a good use of our time right now, but I can do it if we want to skip the next section, because arguably I think it's a little more interesting, but I'll go forward and we can kind of make that decision.
Yeah, because we're actually running.
Yeah, we're running
our
close on time. So the overall solution though is order the processing like this, label the VRAMs label the edges to a VRAM using this generator polynomial. And then also we found that in the VRAM itself, the address of the edge can, if we just shift by k, or this should actually be lowercase k. If we shift that edge by k, we can always have a unique address for each edge in the VRAM. So the final hardware structure with the changes kind of now looks like this. The overall, the top level module is still the same, but inside now we have k VRAMs, and since they're all addressable VRAMs like RAM, we kind of need a bus for reading and writing. The state modules, we instantiate k over 2 of them, and then they have 2 inputs to them, which correspond to the edges that they're processing. They do the merge sort as before. They get fed into the edge modules, which do the edge metric computation, and then those get written to memory. And that every cycle this flow kind of happens until we finish the time point, and then we go to the next time point in the trellis. So the current steps, we're still kind of in the like verification and simulation in hardware part. We want to do this, make sure there's no like timing errors and the behavior makes sense before we actually try and run it on the FPGA. The goal overall is to kind of show that this hardware design actually uses less resources than the previous design and is more efficient. Yeah, and so in the future, if this architecture works well and is efficient, we can kind of use it as like a computational core for these CRC-aided table-binding convolutional codes in simulation, and we can also compare their performance to other codes that the group is simulating. So yeah, this next section is actually that was kind of half of my work here. The other half was kind of done in implementing a noise generator for FPGAs also. Should we continue with this, or would you guys like to see the proof kind of for the encoding? I think
What's up to Amael and Linfong, which would you rather see? The
yeah.
noise generation technique or the proof of how the memory is managed? I think Amael has a clear choice. Go
I
ahead.
think I go for the
Noise generator.
Yeah, let's
We'll
do
do
the
that.
noise generator.
Okay. So big picture, I guess, in the whole pipeline of transmission, we have a message that we encode, and then it gets transmitted over some kind of noisy channel, and then the decoder receives it, decodes it, and then outputs a message. So if we wanted to simulate this, we've been working on accelerating the decoder, because that's actually the most computationally expensive portion of this whole pipeline. But if we wanted to simulate this, what would end up happening is this part would be extremely fast, but this whole section of the pipeline kind of bottlenecks our speed, right? So an overall goal might be to take this entire pipeline and put it on a FPGA and hardware accelerate every part of it. So
That is our goal.
that is our goal.
Yeah.
So at the end of the day, the next portion is kind of dedicated to how do we make this middle additive white Gaussian noise section implemented on an FPGA. So this implementation is also basically entirely based on this paper that's referenced. The overall thing is a uniform random variable is very easy to implement in hardware. There's something called like a Towsworth generator that's been researched a lot, and that's a very simple thing to do in hardware. But to make a Gaussian distribution is a little more complicated. What this paper does is it takes this thing called a Box-Mueller transform, which is a transform you can do on two uniform random variables that ensures that the output are two sampled Gaussian distributed random variables. The issue with this that makes it complicated to implement in hardware is in hardware on FPGA, all we really have are things like adders, shifters, multipliers. We don't have the ability to do like square roots or lns or cosine sines. So those are all functions in this transform that are very nonlinear. So implementing that in hardware, we have to do some semi-fancy things to make it actually accurate. So the paper kind of goes over this. So overall, what we do is we do what we always do, which is we segment a nonlinear function into linear portions. The thing is though, if we were to do a naive linearization where we take the domain and we split it evenly into segments and then linearize those segments, it'll be very inefficient, or it'll be very inaccurate, because the functions in the Box-Mueller transform have extremely highly nonlinear portions, like especially at 0 and at 1. So what this paper says is, okay, instead of segmenting it uniformly, how about we concentrate the segmentation of the domain at the portions that are highly nonlinear. So in this, like near 0 and near 1, there's a high concentration of segments such that those segments are linear, but the like density of those segments at those points are very high. So there's like the method of how we segment this is slightly complicated, but it's like actually simple to do in hardware. I haven't really included it here, but if you want to know more, the paper does a really good explanation of it. So that's it. So that it kind of performs this segmentation on F, and then similarly another these two G functions, the sine and cosine, because of symmetry, we can kind of only just look at like one of these regions and try and approximate this in a linear way. And by doing that, we can kind of recover the entirety of G1 and G2. And then both of these in unison allow us to approximate the Box-Mueller transform. In hardware, this is kind of the overall hardware structure, where on the first stage is the generation of the uniform random variables, which is just a Towsworth generator. Those inputs get fed to the approximations of F, G, and U. So, sorry, actually, I should probably explain this a little bit more. So in hardware, what happens is, so in something like Python, we can perform this segmentation and find the coefficients and the coefficients of those the piecewise linear approximation. We can store those coefficients in memory on the FPGA, and then whenever we want to find like the approximate value of F, we just take our input, we find the associated address for that input. That address will tell us the coefficients of the linear approximation in that segment, and then we take the input and then apply the linear, or get the value based on those coefficients. So that's how F and G's are approximated, and then the Towsworth or the Box-Mueller transform, all you have to do is really multiply those outputs and then That's stage 2. The stage 3 is so the stage 3 and 4, since the goal is to kind of like output a noise value every cycle, what stage 3 and 4 do is they kind of alternate the outputs and also have this accumulator stage that has like a mini implementation of the central limit theorem, but it's just like adding 2 at a time instead of adding a lot. But it is shown that doing this improves the accuracy by a little bit, and it allows us to get rid of these square roots in the function. Like in the function multiplication, or in the G1 and G2.
What do you have these papers that you published?
I can actually find that for you. I want to say in the 2000s.
You have,
Yeah.
you have the reference of any point of this, not show them the publication. Will be, yeah.
Oh, I don't have it written. Okay, sorry, but I'll tell you. I'll let you know after it's over. But that is pretty much it. We implemented this at CSL, and these are kind of some plots. The first set are the errors in the function. So this is kind of showing that the approximations that are made are pretty accurate over the entirety of the domain. This is the F function. You can see it's like it's very small. And then similarly for G1 and G2, they're also extremely small. Yeah, and then overall, this is kind of the transformation that's done. This is like, these are outputs from the FPGA itself. So this is kind of the uniform random distribution that is generated. And then after doing the implemented Bloch-Muller transform on the FPGA, this is kind of the distribution that we get. So, which is beautifully Gaussian distributed. So yeah.
So the left is the samples of the uniform.
Yeah.
Do you have a Gaussian on the right to compare to your distribution?
It's fitted.
There?
It's there. It's
The
fitted.
map is pretty
Yeah.
accurate.
Yeah.
Yeah, but the tail is important, you know. If the tail matches or not.
Yeah. The tail is probably the trickiest portion, I think, because at the very fringes, I think due to the quantization, it kind of breaks a little bit.
Add a magnified law.
Yeah, to shows the tail. Yeah, I agree. But yeah, that's pretty much it in terms of the noise generation. I'd like to thank Professor Wessel, also Professor Potty, for allowing me to do this thesis. I'd also like to thank Chester Hulse. He's been a big source of help and a big inspiration for all the changes done for the list decoding portion. I'd like to thank Adi and Daniel, who've been working with me so far, and also all the other CSL undergraduates that have had a good time.
Thank you very much, Josh. And yeah, we're really looking forward to seeing this project come to completion.
Yeah.
To build the working FPGA list decoder. I feel like we're close.
No, yeah, we're very close.
Okay, thank you very much. I'm going to
yeah.
stop recording now.